Okay, we're back. So it turns out the audio works just fine. It's something to do with when you use a Bluetooth microphone with OBS, it goes into some mode that blocks desktop audio for whatever reason. That kind of sucks. I will fix that at some point, but it doesn't matter right now. All right, so welcome back to the DX12 streams. We are hopefully going to actually finish up our refactoring push today, and we'll get started on some actual renderer work. Hooray! So on the plans for today is that we need to go and finish up the descriptor allocator thing that we were working on last time. We're going to sort of stick our fingers in our ears about the problems we were seeing last time. We're just going to assume that like shader visible heaps will always allocate in just blocks, whereas the storage heaps will always be individual allocations. So we'll have to have two paths through that function, but that shouldn't be too big a deal. It potentially limits some optimizations in the future with like, hey, I know I need to allocate, 6 SRVs for this material. Let me just allocate them as a block. Well, that's not going to work now, but we can go back and make that work in the future if we need to. Now, in practice, like once you get into the notion of being able to free things from a pool without just like resetting the pool, then the block allocation style gets really tricky because it's very easy to get into a situation where like your entire pool is fragmented, and so you're trying to allocate 5 in a block. Well, your largest hole is 3, and you can't do it, even if you have enough descriptors left. So we're not going to bother. We're going to assume that that's not going to work, and it should be fine because the only thing that actually requires adjacent descriptors is the descriptor table bindings, and those are in the per frame shader visible heap, which we just block allocate from and then just nuke the next frame, or well, the next time that we get back to that buffer of the frame. So, I guess let's get started. So, off stream, I went and wrote up this little bit vector structure. I guess technically it's not a bit vector, rather it's a bit allocator. But it's fine. We can expand it in the future to act like an actual bit vector if we need it to. But so why did I do this? Well, we're going to need a bit vector for our descriptor heap stuff, but in the future, we're going to need a whole bunch of these. So in general, with real-time applications, the fewer things that you actually allocate, like the fewer calls to malloc underneath whatever you're doing, the happier you are. Because memory allocation and freeing is kind of slow, and more importantly, it relies on a lot of, like, by doing, arbitrary heap allocations, you have to track a whole lot of object lifetimes, which kind of sucks. It's one of the hardest things to do, especially in a rendering case where you have to defer all of your destroys. And so the fewer things that you have to manage the lifetime of, the happier you will be. So we're going to end up using object pools for a significant number of our rendering things. So, like, any case where you are anything where you might allocate something, every frame, or, well, every frame is a different case, because then you can just do a linear allocator and nuke it at the end of the frame. But if you have something that's, like, you're going to be allocating them pretty much every frame, but they might have lifetimes that extend beyond the frame. So things like command buffers, or, a thing that came up at work a while ago was our little shadow request metadata struct for handling shadow rendering for lights. You don't want to be allocating those randomly, but you also, you might have a lot of them, too many to put just a static array on the heap or on the stack, and you may have lifetimes that need to go across frames or arbitrarily long, right? So linear allocators don't work. And so for those, you want an object pool. And to do an object pool that is fast, you kind of need a bit vector. So that's a long-winded way to say that I decided we needed to have a bit vector class. So this does pretty much the same thing that we were doing before. The gray vector full of, Glockbirds, 64-bit integers, and fill it with zeros, then go through and allocate bits. You return an integer index into the bit vector. If that index is -1, then we failed to allocate. And the only time that we should fail to allocate is if the bit vector is full. So if all of the objects are in our pool have been allocated, we're going to fail to allocate. But that should be the only time when we fail. So we just notify higher level code, and it can figure out what to do. Because you can imagine a case of like some LRU caf where it says, hey, I haven't used this object in a while, so I'm going to free it to make up space. Something that high-level code has to make the decisions about. Okay. So with that, we're going to get rid of our attempt to do this last time, which is going to build and let compiler tell us what we need to change. Actually, we're going to go ahead and okay. So we're going to say that shader visible heaps are always block allocated rather than bit allocated. So we'll leave the bit allocator null in that case, and that'll be our indication that, hey, this is something that needs to be block allocated. So here, create a bit vector, our capacity, then that all goes away. You also need to now free that bit vector. All right. I think the allocate function is the last thing that really needs to be addressed. Yeah, all right. So, what we actually need to compute is this heap index. And when we are bit allocating, we can only allocate a single descriptor at a time. So, because our descriptor handles don't actually work for, like, we're only returning one handle. So we can get away with that in the multi-case for block allocation because we can just say, okay, here's the first descriptor in this in this allocated block, but in the bit allocated case, you may not allocate them in a block, so you would need to return multiple descriptor handles, which we don't really have the capacity to do right now. Like, we can do it, but it'll be ugly, and it's not worth it. So we'll just assert that you're only allocating one descriptor here. Then we will say that vector allocate bit. Here we're just going to assert that we got a proper, like that we successfully allocated a bit, because there's nothing really we can do if we fail here, because higher level code requires that descriptor handle to exist, and at this point, like, we could potentially do something where we chain heaps together, so you have, here's heap A, and then when we fill up that heap, we'll allocate a new heap, and we'll have a linked list of heaps that we allocate from. That gets tricky, so we're not going to do that. Mostly gets tricky because you have to bind descriptor heaps before you render with their descriptors, which is still something I find kind of weird. But we could probably get rid of it for storage heaps, because those never actually get bound. In any case. So, if we get this far, we have successfully allocated, let's say, heap. So the rest of this should be fine. Because if we have a bit allocator, we'll keep the heap index this way, otherwise we'll commit it this way, and the rest of this code doesn't care about how you got the index, it just cares, what that index into the descriptor heap is. So that should be fine. In fact, we don't need a temp here. All right, that's good. Let's see if we build correctly. All right. Now the real question is, do we run correctly? No. I should hit retry. Let's try this again. I messed up allocation somehow. Let's see. What heap is this? RTV heap. Okay. Okay, clearly my allocation function is broken. Let's see. Am I remembering how bit scan works? Okay, this returns non-zero if we find the bit. We're using the inverted mask because we have to so this finds set bits and we want to find free bits. We compute the local bit index by taking the return value and subtracting 1 so that we go from a 1-based index to a 0-based index. We get the global bit by local bit plus I times 64, because we have 64-bit words and I is the word index. Check against capacity, otherwise we set the bit and tag our allocating index as this global bit index. I don't see how this fails. So set a breakpoint and we will try again. Interesting. Okay, I must be misremembering. I guess this already is a 0-based index. Could have sworn it came forward did one-based bit indexing. Maybe I'm getting like git scan forward and find first set. Next up, that weirds me out even more that like it's giving me like just takes an unsigned long. Like, why not take a signed integer here? You don't need the extra bit because the largest word you're going to work with 64. Okay. Let's see if this works. Seems to. Okay. All right. So we have a descriptor allocation that pretty much works. So that's cool. Okay. All right. So that, I think, will let us drop off that for now. So the next thing to do is do some split passes for our lighting. So what do I mean by that? Right now we have like our frame is that we render directly to the swap chain. And then we present the swap chain, and then we're done. Nice and simple, but it unfortunately has a bunch of problems that come up. One is that there's a whole lot of fancy post-processing that you would like to be able to do that requires spatial knowledge of the screen. So things like doing screen space reflections or even just the bloom requires that you can basically blur the screen for some definition of blur, right? So in order for that to happen, you need to be able to access the target after you have rasterized the scene, or in most cases after you have lit the scene, and you need to be able to then do work to it before you get to the swap chain, because once you get to the swap chain, you're basically done. You can continue to render onto the swap chain, you know, if you wanted to do something like composite UI on top, but you can't really do something where you like render to the swap chain and to do a post-processing pass that reaches from the swap chain and then render back to the swap chain. That's not going to work. So that's part of it. The other issue is your swap chain is low dynamic range in almost all cases. So specifically, in our case, because we're not doing HDR in terms of like monitor output, our swap chain is 8-bit RGBA. And so those are unknown values. They go 0 to 1, and you have 256 values there. That's not enough to represent physical lighting values. So for example, when it comes to physically correct lighting, your sunlight ends up being something like 120,000 lux as its intensity. And so, LED does never go to 1, so you don't actually get the full 12,000 or 120,000, but you get some very large values, especially in the middle of like specular highlights. You get the really concentrated energy from the light. So what we want is we want to be able to have our lighting data stored off in floating point texture. We want floating point because we want to be able to have, areas that are nice and dark and also areas that are really bright, right? So you might have shadowy corners and, a really bright speck hit from a flashlight or something, right? Like if you're doing a horror game or something. And so you need to support that dynamic range, but you can't do that with 8 bits. So what we typically do is we render our lighting to a floating point target, usually either 11, 11, 10, or 16-bit. And then you have a time mapping pass, which takes that linear, physically correct lighting value. It applies some basically compression to the dynamic range. That's tone mapping. And then you also usually apply your linear to sRGB conversion at the end of that shader as well. And that gets you a presentable target. And so that's, at the simplest case, that's what a reasonable physically based frame looks like. You have your lighting pass, and then you have your tone mapping pass. And then obviously you can expand on that. So like we're going to do a deferred renderer, well, our lighting pass is not actually going to be a single pass. It's going to be a G-buffer pass followed by a lighting pass. We're going to have post-processing, things like screen-space reflections, which will be their own passes. So you can imagine that there's this long chain of passes that you end up building, and it ends in your tone mapping pass, typically. Again, you can also do things where you do your tone mapping pass and then you render UI on top of it, which is useful in a lot of cases if you want to avoid having your if you want to avoid the memory cost of an off-screen UI target that you then composite. And obviously there are other things you can do, like Viper can render directly to the swap chain for our, we call it present pass. But in a lot of cases, especially on consoles, we actually render to an off-screen target, and then we do our anti-aliasing on that target, and then we do upsampling from that target to the output resolution before we render UI. So you can, that gives you the flexibility to do things like, I've got a 4K screen, but I can render my game at 1440p or 1080p, and it'll be a lot faster. And I can just do fancy upsampling to make it look acceptable at 4K, which is a really useful thing to be able to do, because especially with 4K and the inevitable push for 8K, like, rendering every pixel is a waste of your time. You never actually want to render all the pixels. Alright, so what we're going to do today is we're just going to move our existing mesh rendering to a lighting path that writes out to a floating point texture, and then we'll have a second pass that does 10 mapping and writes to the swap chain. So that should be hopefully that's straightforward. I don't know if it'll actually be. Okay. So to start, honestly, I would like to do the post pass in a compute shader. Just because that makes, like, compute shaders are just better at post-processing a lot of the time, and it also lets you do things like moving all your post-processing to async, can overlapping frames. But we don't have compute shaders set up yet. Let's see. How hard would it be to wire compute shaders into our shader stuff? I mean, let's just do it. We'll have right, this is the C++ file. Okay. That should be sufficient. So we will have compute shader for our time mapping. I will need to refresh myself on how compute shaders work in HLSL. All right, so we'll do 8 by 8 for our threads. You should never ever do a compute shader that is 1 by 1 by 1, not in any real-time context, because the way that GPUs spawn threads is they spawn what are called glue fronts or warps, depending on your vendor terminology, of threads that run in lockstep. So on NVIDIA, you get, you spawn a single warp, you get 32 threads. So that's the smallest number of threads that you can have on NVIDIA. On AMD, it's a little more complicated. GCN is 64 threads. RDNA2 can actually run in 2 different modes. It can be 64 threads or it can be 32 threads. So that's some weirdness. But the point is that you want to have a total thread count that is some multiple of the warp sizes that you're expecting. So in general, you want to have it be a multiple of 64 because AMD is sort of your worst case in terms of thread groups, in terms of array size. But 1 by 1 by 1 is, there are some cases where you don't care, but in general, it means that you are wasting a whole bunch of GPU occupancy on spinning up a single thread out of, 32 or 64 available. So there's one 8 by 8 blocks. So the way this works is the way compute shaders work is pixel shaders are spawned by the rasterizer, right? So you rasterize a triangle and then you spawn threads for every sample point hit by that triangle. And that's all handled by a fixed function. On the other hand, vertex shaders are spawned based on your index buffer, right? So, for it sort of, the input assembler goes through and assembles triangles, and once it gets to 32 or 64 unique uncached vertices, it spawns a wave to shade those vertices, and then it puts the shaded results into the vertex cache. And so that's a little more complicated than pixel shaders, but again, it's something that's the threads that are spawned, how many threads are spawned is not your responsibility as a programmer. Compute shaders are different. So compute shaders, there's basically basically no fixed function in the pipeline at all. There is no pipeline for, right? There's no, like, there's no multiple stages to compute shaders. Instead, a compute shader is just an arbitrary block of threads that execute a program in lockstep, and you can dispatch an arbitrary number of thread groups at a time. There's nothing in how compute shaders work that really forces you to do any one method. Like, there's nothing that says, oh, you're spawning 8x8 blocks, therefore, like, you know, this first thread group handles the 8x8 pixels here, and then the next one does the 8x8 pixels next to it, and so on. Right? There's nothing that forces that to happen. So that lets you do some really cool stuff, like building deferred queues and you know, sort of spawning work groups where you need them rather than where they sort of naturally align, which is really useful. Not something we're going to get into today, but it's, you know, you can do arbitrarily complex things with compute shaders. But in general, we're going to just use, for this case, we're just going to use an 8x8 block, and then we'll use that to basically tile the screen with 8x8 blocks, and we'll load from the lighting buffer and do the time mapping, then store the result in swap chain via an unordered access view. So UAVs are pretty much the only way you can get data out of a compute shader. That's not true. You can have structured buffers that are writable. I think. Maybe that's not true. I don't know. So, linking right into textures, at least, you go through UAVs. So, we need to build our or we need to set up our bindings first, and I don't quite remember let's go look at the reference. So I think we may actually try to use a sampler state that's sort of built into our shader rather than binding sampler. I think we can do that. Alternatively, we can just load, because we're not going to need any filtering. So maybe we'll do that instead. Let's see. I think what we need is a texture B, which is our call it the input. Then we probably want this to be Mr. T0, maybe. We need a rewrite texture to D, which would be our output. We'll call it struct content mapped output. I'll put that in register 1. We're going to try to do this with just texture loads first, for faster on some architectures, but we can go to using a sampler state if we need to. But for okay. I think we can just do load their dispatch ID, and that should get us the HDR color from our lit buffer. So now we have a color value, but its range is not what we expect. right? So like what you want to output is something between 0 and 1. Like even with HDR outputs, you're usually outputting to a fixed range, so 0 to 100 nits or something usually. So you're going to have to do some remapping from your lighting values, which are really big, like 16-bit float can go up to 65,000, right? So you have quite a bit of compression, like in the PSP sense, I guess, that you need to do in order to take your huge range of values and sort of squash it down into 0 to 1. Because specifically, you want to squash it down to 0 to 1 and not destroy the color when you do that, right? Like, an easy way to do it is you just, people could just do that for LDR color equals saturate. That'll clamp the value to 0 and 1. And so, that works. It does what we wanted. It'll get us to, it does what we said we needed, which is that we will get a 0 to 1 output from it. However, this doesn't do what we want, because it'll just chop off like all of your bright colors. So what you actually want to do is you want to apply a curve to this value that remaps it smoothly into the 0 to 1 range. There are a bunch of ways to do this. So the big one in games, the one that everybody uses some form of filmic curve, which is this, just like an S shape, right? So it has a toe that like lifts up your darkest colors to sort of compress those, and it has a shoulder that takes your bright colors and smoothly brings them down to wherever your light point is going to be. And that's fairly effective for doing the range remapping, right? There's an additional thing that we'll run into in a moment, but we'll go ahead and say we're just going to slap a filmic curve in here and call it good for now, right? So John Habel has a really fantastic blog post on various curves you can use for filmic tone mapping. A bunch of examples. We are going to, let's see. So we're going to use this Uncharted 2 tone mapper, which, as you may expect, is the tone mapper from Uncharted 2. So we have this curve, which is just, here's the shape we're going to apply to our colors. And then we rescale afterwards according to the white point. So this may not be what we go with in the long term, but I'm familiar with this curve, so we're going to go for it for right now. But the reason that we may not go for this long term is there's a whole lot of parameters to this curve. Like, it is just, there's just a lot. And so you kind of want something that's a little more fire and forget than this. Like, you can just leave all these fixed, but then, 3 months later, art comes to you and complains about not having enough contrast in their blacks, and now you have to go and figure out how this works. Which is doable, but it's tricky. So if we're actually going to adjust our white point a bit, for like white point of 2, just because I don't think that we're going to have all that much brightness in here. So makes it a little weird that we're using the same function for both, like just passing, like just tone mapping the white point, which is a scalar, and tone mapping the color, which is not a scalar. Flip through. It doesn't actually matter. Like, technically, this is expanding the value to 3 floats and then tone mapping that 3 times. In practice, because we only read the X value out of that, dead code elimination will figure out that, hey, we don't need to do the other 2 tone maps. And actually, in this case, like, W is a compile time constant, so this entire thing is just going to fold down to a single constant. So that should be fine. It's the sort of thing that could be an issue if you are running with unoptimized shaders for whatever reason, but in practice, like, anything that is dependent entirely on compile time constants is going to fold down because the one thing that shader compilers are really good at is constant elimination. Which is easy mode on shaders versus CPU code because literally everything gets inlined, so none of your functions exist afterwards. Anyway, so what's the rest of this curve? Yeah, we take one over the tone map thing and just multiply it into the color. Okay. Okay. So now we have our color that has been time mapped, but it's still linear in a sense. So obviously we've gone from like linear lighting down to a compressed range, but when we output to a display, the display expects a particular curve will be applied to your color values before it outputs. Right? Before you output to the display, it expects you to apply the sRGB curve, and then it will invert that to produce colors for the display. And so in order to get the colors out that we want, we actually need to apply the correct curve here before we output. So to do that, let's see. We need we can do just a approximation like this. This is not actually the sRGB curve, though. So this is very close. Like 1 over 2.2 is actually the curve that sRGB is fit against, but the actual curve is an exponential section, and it has a I guess not exponential, right? Whatever. It's got a curved section and it's got a linear section. And that's for reasons that there are things that you do with color that make a lot more sense if you actually have a valid gradient near zero, which you don't really with just the power curve. So we will look this up because I don't trust myself to get the maths right. Let's see if Wikipedia actually has the right thing. Yeah. So we have this linear section if we're below this value. Otherwise, no. That's backwards. Yeah. Wikipedia. Why? Why are we so bad? Go away. So this is a really good blog post to, if you're interested in why we do sRGB. The reason is that it lets us compress our colors better for the low dynamic range target that we're related to, and so you get better, you get less banding with your values. The other reason you might think of doing this is to, if you want a perceptual color rather than like a mathematical color, this is usually what you would do. So for example, anti-aliasing tends to work better if you have the sRGB curve applied prior to anti-aliasing, because then it will detect edges that are visible in the actual colors that you're outputting, rather than edges that might be visible in your primary lighting buffer but aren't really visible after tone mapping or whatever. After tone mapping and Lisser mapping, right? So it'll find perceptual edges, which is what you want. So there are a couple places where you would use this, but in general, your tone mapping pass is a big one. I'm just going to rename this because I don't like that naming convention. In fact, actually, there's one of the AMD presentations had a branchless version of this. So while it does not matter at all, I'm going to go big for this because I want to. That's this one. This presentation is actually also pretty good. It shows off the reason that you would want to do post-processing stuff in a compute shader, which is you have access to shared memory across your work group, which lets you do all sorts of really cool stuff that we're not going to need for tone mapping, but that is useful. Yeah. Ugh. There we go. So this is just a branchless version of the same sRGB curve. And while branches are not as terrible as they used to be for GPUs or for shaders in particular, there are a lot of cases where expressing something in a branchless manner will help the compiler. Specifically, in cases where your branch is going to depend on some varying value, right? So in this case, a branch there was based on the color value, which is going to change across the screen. And so you might have different threads within a given warp take different sides of that branch. And so that's inefficient because it means that you have to basically run whatever threads take the if case and run whatever, then stop and run whatever threads to the else case and then rejoin afterwards, versus something that is branchless, which is just everything flows through once and you're done. It can make sense to use branches, even dynamic branches, around things like texture samples, where you don't care about wasting a few cycles on a branch because the texture sample is like 40 cycles or something, depending on, do you hit cache or what, right? And I'm making up those cycle numbers. It depends very much on the hardware whether like skipping a texture sample makes sense or not. Anyway. I'm just going to make this be float 3 to float 3, and hopefully that'll work. Okay, so now we need to write so we turn map output P DXY. I'll go ahead and copy across the alpha, just in case we need it. In the vast majority of cases, you will not actually have an alpha channel in your loading buffer. The only times that will happen is if you have, like, you're rendering a 3D object that you want to composite over your menu or something, and so you need to preserve the alpha. We do that in our menus at work. We don't do that in the main game. The main game just uses the 11.11.10 texture format for its loading buffer, which means it's half the size, which is nice. Okay. So, I believe that is a time mapping pass. Now, this will look fine, but this is not actually the best way to handle time mapping. So the reason for that is there's actually two separate things that need to happen when you are mapping from your linear lit color to your output color. Even before the sRGB curve, we're going to ignore the sRGB stuff. So the first thing is tone mapping. And tone mapping in in a stricter sense than it is usually used, is all about remapping ranges. So the goal of tone mapping is to compress the range of lighting values you have down to 0 to 1. However, the secondary issue is something called gamut mapping. Now, gamut is sort of like the range of colors that are actually covered by your color space. So think of it like this. When you have, there's this concept of luminance. Which is roughly that. I mean, there's definitely more digits to this value that you want to have. You want to actually compute luminance, but that's roughly the ratio. And so luminance is sort of how perceptually bright a color is. And so with LDR values, with LDR values, 0 to 1 in your color channels, your luminance is going to range from 0 to 1. So the only color with a luminance of 0 is black. The only color with a luminance of 1 is white. So you can imagine that, let's say that you had three bright lights in your scene. So let's not even do lights. We'll do you just have emissive cubes, they're full-on neon emissive cubes, and say one of them is green and one of them is blue, and just completely saturated green and blue. And they have the same intensity, right? Well, the green one is going to appear significantly brighter than the blue one. And in particular, when it comes to tone mapping, the green cube will hit its luminance ceiling and start compressing before the blue one does. I'm not explaining this very well. The idea is you want to preserve as much as you can, the relative luminance of different objects in the scene, right? So let's say that in the lighting buffer, both the green and the blue cubes have a luminance of 1 prior to tone mapping. So you want to preserve that ratio. You want them to both look equally bright. But of course, a luminance of 1, the only thing that's allowed to have a luminance of 1 in LDR colors is white, because, you have to have all of your color channels maxed to hit 1 with this. So when you remap to if you say, okay, we're going to remap to the brightest color in each channel because we're clipping, then green looks pretty bright because it's, it clamps to like 0.07. But blue ends up really dark relative to the green because you can't represent a luminance of 1 that is blue in FDR color space. Well, not this LDR color space at least. So that's kind of unfortunate. And so what ends up happening is different colors of light that are approximately the same intensity will have different appearances, will appear to have different brightnesses. So when we pass them through this tone mapper, and you'll notice that like right now we're doing this tone mapping on each color channel individually. So for really bright colors that are not fully saturated, right? So you have some amount of color in each channel, but maybe one of them is a lot higher. Maybe you have a color that's like like a really bright green. Well, when you tone map this, this central channel is just going to click. It's going to hit your light point and it's done, right? Whereas these other channels are going to not be compressed as much. So in terms of the ratios, the rest of your colors rise up to meet your brightest channel, right? And so the result is you get a desaturated version of your color. Now, where this gets tricky is say we have something like this. So red is right at the white point, the green is way past the white point. So in general, this is a slightly yellowish green, but it is very much green. When you tone map this color, it turns yellow. Because both the red and green channels will clip, and as a result, you will get 110 in your colors, and so it's full red, full green, that's yellow. That's obviously not what you want, right? Because that just makes things look weird when, you can imagine you have like this bright, slightly yellowish green cube that sort of pulses its color, right? And so it'll go from green to yellow, not because it's actually shifting to yellow, but because it's getting too bright and the tone mapping is clipping and destroying the hue of the color. So trying to preserve luminance and hue is something we call gamut mapping, which is remapping colors from outside the gamut into the gamut of like representable colors in your output color space. And it will always, 100% of the time, be a trade-off. So you have your luminance, you have saturation, and you have hue. And one of those is going to go away. like one of those is going to break, just because you have to in order to do this compression. So typically, you want the saturation to be where everything goes, right? You want, if you have a really bright object, you want it to desaturate when it gets bright, because that's kind of what actual, that's what the cones in your eye will do. It's what sensors on a camera will do. If you're looking at a very bright object that is some color, it's going to look desaturated versus a darker version of that color. And the reason is just like when it's really bright, it overstimulates sensors, which ends up bleeding out and stimulating adjacent sensors. And so in both your camera and your eye, like, you've got a mix of colors around each point. So, when you stimulate adjacent sensors in your eye, it's not just going to register as green, it's going to register as red and blue as well. And so really bright objects look desaturated because they overstimulate the receptors in your eye or sensors in your camera, and you get like color bleed from that. So people have this built-in innate response to, hey, this really bright thing is desaturated. So when you see something that is desaturating, like you see something that has like a green glow around it, but it's right in the core, like a lightsaber, that looks really bright. And it looks really bright because you mentally associate a desaturated core with something that's really, really bright. So desaturation is kind of desirable in terms of tone mapping. In terms of like tone mapping your clipped colors, you want them to desaturate. But you definitely want to preserve hue, right? Because you don't want your lightsaber to turn yellow towards the center, right? Having a gradient from green on the bloom all the way to yellow in the core looks weird. So that's not a thing that you want. So you want to preserve hue as much as you can. You also want to preserve luminance, because you want your red lightsaber and your green lightsaber to be approximately the same brightness, right? Without an artist having to go in and say, oh, well, this one's red, and you know that red is an inherently darker color, so we're going to have to crank up the emission on that. As well, you can do that for like authored assets, even if it makes your artist unhappy. Can't do that for things like player-created content. The player can just bring up a color picker for their lightsaber, right? You can't then easily normalize the emission. Right? You kind of can. You can compute the luminance of the color before you and use that to rescale, but you don't want to. You want to just have, okay, this is X brightness, and the tone mapping will just do the right thing. So, generally speaking, you can preserve hue by computing the luminance of your HDR color, tone mapping the luminance, and using that to rescale your HDR color. And that will apply the curve to all three channels at the same time So you won't get any hue shift. Downside to that is that you won't get any desaturation, which you want, because otherwise things sort of clamp out where they look not dark, but not really bright either. So what I started doing at work is like time map the color channels individually, figure out how much it desaturated, then time map luminance and manually desaturate the color. Because then you preserve the hue and the perceived luminance. And then there's an extra bit of, if you're clipping, you have some minimum desaturation applied to handle cases of, I have a bright primary color in my frame buffer that doesn't desaturate at all because you're just mapping green to less green or something like that. So you can manually desaturate after the fact. Having done that long-winded explanation stuff, we're not going to bother with that right now. We're going to wait until we get into a situation where we care, because then it'll be easier to demonstrate the issue and be more methodical in fixing it. Okay, that was a lot of talking and not a lot of coding. We're like 2 hours in. Okay. Okay, let's make sure that we can actually get our compute shader loaded. So load shader. Shaders. Time mapping. HLSL. Okay. Right, we have to specify a format for this. Remind me how this works, please. what I need. Maybe not. Right. UAVs are a different thing. Okay, it doesn't like this being a global scope. Not sure why, but sure. Missing entry point. That's interesting. Right. Right. Yeah, alright. That should do it. Okay. Before shader compiles, so now we kind of have to do a whole bunch of stuff all at once, which is not awesome, but kind of how it is. So we built our depth texture here. So around here is where we're also going to build our lighting buffer. And we're going to go with 16-bit float here, just because it's easier. We'll have better luck with precision in 16-bit targets compared to the packed float targets. Like you're not going to have as many issues with like hue shifts because you can't have as much precision in the blue channel and whatever. So this is going to be used as an RTB, and also going to be used as an SRV because we need to read it from the compute shader. So this is just going to be the same. So we will just copy it over. So we will have an RTB and an SRV for this. Okay. Make sure that this step runs. Does. Great. And for the record, this is not how we're going to handle like building render passes in the future. We're going to do smarter, more abstract things, but for now, we're going to do the most straightforward version of this possible, just so that we can get something done. All right. So our format for our rendering, our PSO is going to be things are laying but buffer config. We also need to do same thing where we destroy and recreate the lighting texture on resize, just so that we get the updated size. actually reminds me that we fixed descriptor allocation. We did not actually add descriptor free. That's not great. Oh well. Let's see. Our swap chain. Well, let's finish this up first. All right. We're unlikely to resize enough for it to matter right now, but that is something we will probably need to fix next time. So our swap chain is no longer used as an RTB, or will no longer be used as an RTB. So we need to tag it as UAV instead. So the rest of our frame is actually broken now. So we have to fix all of this before we can even test that we got things right. So this will be interesting. But we need can change our barriers here. Still weirds me out that like pixel shader resource and non-pixel shader resource are like different. Okay, so I think it's high time we fix this. Right now, we try to determine what state to create the texture in based on like its usage flags, but we can't actually because there's, like in this case, pixel shader resource versus non-pixel shader resource are two separate states, whereas an SRV could reasonably be for either. So I think what we do is we look this and we just have we have the user pass in what state they want this to be created in when they create it. Because I think that's just better. High-level code knows better what state it should be in. This should be created in non-pixel shader resource because that's sort of our default state for the lighting texture. We're using common for the texture, which is not really what we want, but it's fine. All right. So our lighting costs should be reasonable here. No, it isn't. We need to get there we go. I'm sure we will discover bugs, but I think this is correct now. But now we need to handle the compute pass. In order to handle this, we actually need to build a compute pipeline state. need to build out our compute pipeline before we can actually bind it. So tell me what's in here. We need a root signature, because first we do. Yes. There are other node flags. No. We'll need to create that root signature. Shouldn't be too hard. Yes is all right. So we need two descriptors here. These are not terribly good names. It's just do the easiest thing. We will make all of this nicer in the future, hopefully. Yeah, so texture first. Unity second. I'm missing something. Right. I need to put a root parameter from this. This whole song and dance is kind of annoying. Okay. Put a breakpoint here and see if we crash before we get there. We do. Oh no. Right. All right. So I would need to go and actually decode this H result to know for sure, but I'm pretty sure what we're running into is we're asking for UAV access to the swap chain, and the GPU is saying no, you're not allowed to do that. Which is the thing that it's allowed to do. And I'm guessing it's because we're not using the correct texture format here. Our swap chain format is RGB-A. So maybe BGR will do better. No. Okay. Well, that's disappointing. Apparently we can't use the UAV to render the swap chain. So we could work around this in two ways. One is we could do the last pass in a pixel shader, which isn't terrible. Or we could write to a intermediate texture and copy the swap chain, which is also not fantastic. It's another texture that we have to allocate, and it's another copy that we have to do. That's very weird. I know you can bind a swap chain texture as a UAV on Vulkan, though there is a bunch of songanames to get that to work as well. Alright, well, this is going to take some work to get functional, and I've been streaming for a bit at this point, so we'll go ahead and call it here. Maybe next weekend we will actually get through the nonsense with swap chain, UAV stuff. I'll take some research, figure out if there's a way we can ask nicely for UAV access to the swap chain. But for now, I think we're going to call it. See you next time.